Next speaker is Ying Zhao from Institute of Advanced Studies in Princeton. She's around, I hope.
Yes,
Ying, can you share your screen with us?
Let's see. Does this work?
Yeah, we can see that. Yeah, so she's going to talk about her work on Petz map and Python's lunch. Please take it away.
Okay, thank you. Hello, everyone. Thank you for giving me the opportunity to give a talk here. I hope everyone stays safe and healthy in this very special time. Today, I will talk about some recent work on Petz map and Python's launch. Roughly speaking, I will discuss the complexity of Petz map. Here is the outline of the talk. I will first give some motivations, and then during the second part of the talk, I will try to show how to write Petz map as precursors. So in this talk, I will use the word precursors in a flexible way, in the sense that, let's say, if we say WA is a precursor, I mean WA can be written as some utility, W utility dagger, where this utility is a unitary operator. It may or may not be generated by a natural black hole time evolution. W is a simple unitary operator. So I will show that Petz map, under the condition of perfect recovery, it can be written in this form. Once it's written in this form, first of all, it's clear it's unitary. Second, one can estimate its complexity. It's clear that most of the complexity comes from the unitary evolution utility. And then we will look at the complexity of Petz map. I will discuss two different situations. One situation is that the trivial situation is that when you try to do the reconstruction while having the entire system in your hand. The more interesting situation is that, say, we lose access to part of the system, but somehow we can still reconstruct the operator. Petz map showed us how to do that. But in this case, the complexity can be much higher. In this case, it's related to some earlier work from the end of last year. It's about we'll see that Python's launch will appear. And then I will give a summary and give some comparison between interior and exterior operator reconstructions. So first, let's review what we know well about operator reconstruction, let's say inside causal wedge. Inside causal wedge, one can use HKLL reconstruction of a bulk operator. Let's say, imagine, can you see my mouse? Hello?
Yeah, we can see your pointer. We can see your pointer, yes.
Okay, thank you. Let's say this line, here I draw ADS geometry, empty ADS geometry. And this line represents R equal to 0. This line represents R equal to infinity, where R is the radial coordinates labeling the transverse area of a sphere, transverse sphere. For some operator here, let's say at the arbitrary bulk point, we can solve the wave equations in the bulk and write this operator as a smeared operator in an interval like this on the boundary. And once we write this operator as a superpositions of the operator on the boundary, for each operator on the boundary, our goal is to write this operator as a write this operator as some operator here at a particular time on the boundary. Let's say for operator at different time, then we can use do Heisenberg time evolution to evolve it back. And that's roughly the idea of HKL reconstruction. One feature one can see that is that, say, in empty ADS space, if you move this operator, say, deeper into the bulk, this interval will get larger, but it never gets too large. The complexity of operator reconstruction in this form was studied by Lenny Sutton in 2014. Complexity of the operator is defined as the number of simple gates needed to apply this operator. Let's say we imagine we want to reconstruct the operator here. I have a smear operator here. And for any operator here on the boundary, let's say that this is t equal to 0. Eventually, we'll write all the operator here as some as Heisenberg evolved operator at t equals 0. It's clear that as this interval t gets larger, the complexity of this operator will get larger. So one sees some kind of layered structure here that as one goes deeper and deeper into the bulk in radial direction, this interval will get larger. So the complexity of this operator will increase. In particular, let's see if we say have a black hole in the bulk, and we imagine what will happen if we move this operator closer and closer to the horizon. What one will see that is that actually the length of this interval will blow up. To be more quantitative, the length of this interval here, t, roughly goes like beta over 2 pi times log of a over delta a, where a is roughly, say, the transverse area of this point, or as one approaches horizon, is roughly given by the horizon area. And delta a is the area difference between this point and the horizon area. It's clear that there's logarithmic divergence as one approaches the horizon. So naively, it looks like complexity blows up as the complexity of operator reconstruction blows up as one approaches the horizon. So this is what we learn from HKL from about the operator reconstruction in the exterior of a black hole. But on the other hand, from earlier work during, say, the past couple of years, we know that operator reconstruction in the interior is actually still possible from some work on, say, quantum error correction, JLMS, Petz map, modular flow, etc. Then it's natural to ask how complex it is to reconstruct an operator in the interior, and what happens to this naive expectation that the operator complexity blows up. In this talk, I will try to answer the question from the point of view of one particular way of reconstructing the operator, the Petz map. But before we go into details, let's just get some intuition from some, say, earlier work. From the past few years' work on, say, holographic complexity, complexity volume duality, or complexity action duality, there is one very basic idea, is that the minimal circuit preparing the state is stored in the interior. I mean, in this talk, I will call this horizontal circuit for the obvious reason that it grows in the horizontal direction in a normal Penrose diagram. And let's say we want to apply operator here somewhere in the interior. Then it's natural to expect that at least one needs to undo the time evolution in this, one needs to shorten the wormhole and undo the gates stored in the circuit in the interior. Then one can apply operator. Then one can go back. That's just a very naive guess. And so we will see that under certain circumstances, this is essentially what Petz map does. And we will, and also from this, one can sort of have some expectation about its complexity, that it should be related to, say, how deep this operator is located at. Again, this relation is only true under certain circumstances, as we'll see later.
Ying Zhao, can I ask a question?
Yes, please.
Yeah, so when you talk about this operator complexity, it is the evolution of from the identity operator to this operator, or is it the evolution from the boundary operator to this bulk operator?
I assume the boundary operator, simple boundary operators as simple. And then it's a kind of complexity is defined as how many simple operators do you need to reconstruct this operator.
Okay, thank you.
Yeah. So from this intuition, one see that to some extent, the operator, the relation between operator complexity and radial location still holds in the sense that operator deeper in the interior, we expect it to have larger complexity. Are there any questions? Okay, then let's talk about Petz map. Petz map, I will use it's a specific form given in these papers from last year. So here's a quick review of Petz map. Let's say Petz map will use the knowledge of the embedding of the co-subspace into the boundary CFT Hilbert space. Let's say we denote V, we denote by V of this embedding. And let's say we want to apply operator W on the co-subspace, but we only have access to subsystem A. We trace out subsystem A bar. This is what Petz map told us to do, at least in the notations in these papers. So it's made of 3 parts. In the middle, we conjugate W by this embedding operator V. Then we trace out A bar. And then on 2 sides, on both sides, we multiply this operator by sigma A to the power -1/2. What is sigma A? Sigma A is so pi code is the projection on the co-subspace. Then again, we trace out A bar because we see that for each part, it only depends on A because we only have access to subsystem A. We trace out A bar. And the pi code in this case can be written as V times V dagger. So if we look at this operator, I mean, it's not clear if it's unitary because it's a multiplication of 3 parts. None of them are unitary. But as we will see, under certain circumstances, in specific, it's under the condition of perfect recovery, we will write the operator in a form that looks like a precursor, which first of all, it shows that it's unitary. Second, we will estimate its complexity. I will do this by studying a couple of simple examples. Let's say we start from the simplest example is a perturbed thermal field double. We model thermal field double by a bunch of Bell pairs, let's say S Bell pairs. So we write the state like this, where I labels the microstates of the black hole, and we have 2 sides, A and B. Then at some point, I throw in a spin from Alice side. I use A to label the state of the spin. This psi 0, this state is the state after the spin just foreseen. And then I do time evolution. I do time evolution on Alice side. Here is the new state. And AI is evolved to I, U, I, AI, where U, I use U to label the black hole, natural black hole time evolution. And at this point, the task is that we want Alice to flip the spin. In particular, let's say if initially there is spin plus, now she wants to flip it to spin minus. What's the operator to use? I mean, again, we look at this V, this embedding of the co-subspace into the boundary Hilbert space. In this case, is HA times HB. Here, this is what the embedding looks like. I won't go into the details here because it's really simple, but one can show that if you just follow the definition of Petz map, in this case, W of the reconstruction you need is exactly UW dagger, as one can guess. Clearly, what this operator does is to undo the time evolution by U dagger, apply the operator W, then do the time evolution again. But then there is one immediate question: what is U? In general, we don't know U. What we do know, what we do have is some knowledge about the code subspace. But in this case, the code subspace, let's say we have one spin, a two-dimensional code subspace, but then we trace out B system. So what we do know is this matrix, let's say this is V of A and V of B. We trace out B, and what we do know is this matrix. We know this, but it doesn't tell us what U is. However, if you observe it a little bit, you will see that the operator we need is exactly the matrix element WAB times MAB, where MAB is this matrix. So another thing we learned from this example is that the knowledge of code subspace doesn't tell us what the operator U is. It doesn't tell us this entire horizontal circuit. But if we want to flip the spin, it tells us what this precursor is. Let's look at another example, pure state black hole. Let's say we have initial state. Initial state, I use this capital I to label a particular initial black hole state. We know that this state is made of, let's say, S-1 qubits, and has a yin. And then we throw in a spin. Again, I label the spin states by A. Then again, we do some time evolution. And after time evolution, we divide this S qubits into two parts, A and A bar. I label by I and alpha. Eventually, we will talk about the operator reconstruction when we only have access to part of this, say A. The goal is the same, that we want to apply the operator sigma x on the spin. We want to flip the spin. And here's the embedding of the code subspace into the boundary CFT Hilbert space. We have one spin and a two-dimensional code subspace. And later, I will use the notation that the image of this code subspace in the boundary CFT Hilbert space, I will call this E of AI, where A labels the spin, where A labels a spin state and I labels the initial states of a black hole. I mean, this state is one state in the boundary Hilbert space. And we have some knowledge of code subspace after we trace out the A bar. We first look at the simplest case that we keep the entire system. So what we mean is that we assume A bar is empty set. We see what do we get. Again, in this case, actually one can guess what do we get. One can guess that we still have something like UW, U dagger, basically undo the time evolution, flip the spin, then do the time evolution again. But from this form, it's not clear that this is what Petz map does. We first look at the middle part. We don't have this trace A bar because A bar in this case is empty set. Then we have something like this. This looks like UW dagger as what we want, but if you look at it more carefully, this is not a precursor. This is not UW dagger. The reason is we can write it like this, E of AI, where I remind you that this E of AI is the image of A is a particular, of a spin A state is a particular state in the boundary CFT Hilbert space. And E of BI, this is a cat and bra. And in the middle, I insert a matrix element WAB. However, we have a summation over this spin index, but we don't have summation on the on capital I on the black hole on the black hole microstate because we have fixed initial state. So an operator like this is not a precursor. Then we look at there are two parts here, sigma A. In this case, sigma A is nothing about the projection to the co-subspace. Again, it can be written as something like this, cat and bra. We have a summation over the spin index A, but we don't have a summation over this capital I. Let's pause for a little bit and look at the answer we guessed. The answer we expect is something like this. It almost looks the same with this, but not exactly the same. The difference is this precursor, if we really want a precursor, we actually need a summation over this black hole microstate J. However, if we multiply this from both sides by pi code to the power 1/2, we get exactly VW V dagger. So then what PathMap told us to do is to, let's say, this VW V dagger multiply pi code to the -1/2 on both sides is exactly UW dagger. So in this case, I mean, the PathMap looks like it has a complicated form. It's made of 3 parts. None of them are unitary. But when combined together, if you keep track of the indices carefully, you'll see that it's actually a unitary operator given by UW dagger. The more interesting case, of course, is that when we trace out part of the system, say, let's say we do this. This is our initial state, black hole state, initial state I, and then we throw in a spin which is labeled by A, and then we apply U is the black hole time evolution, and so we have 5 qubits coming in, and out of the 5 qubits coming out, I only keep 3 of them, I call A, and I throw away the 2 of them, I call A bar. So then the goal is I still want to flip the spin, but now I only have access to part of the system, A. The similar problem was discussed by Hayden and Presco in a beautiful paper years ago. And the conclusion is that, let's say, first of all, we assume this unitary U is random enough such that we can treat it as a perfect tensor. What I mean is that if we divide the indices into 2 parts, then there is an isometry from the smaller part to the bigger part. And the condition is that, here's the condition. If this condition holds, basically what it says is that the dimension of A bar and the spin together is less than the dimension of A. When this condition holds, then what Hayden Presco told us is that the spin is still encoded in subsystem A. So if you want to flip the spin and you only have access to subsystem A, you can still do it. And one can work out, in this case, one can work out what the PathMap does. The algebra is a little bit more involved, but the essence is basically the same as we just saw in the case of when you keep the entire system. The important thing is to keep track of pay close attention to the indices, that which part you sum over, which part you don't sum over. And after all the smoke's clear, you will see that PathMap can still be written in a precursor form as U total, W, U total. But this U total, first of all, it's certainly not U. Imagine that W of A only acts on A subsystem. So U total is a unitary operator on subsystem A, and it's not the same as U. Here is the definition of U total. Let's say I have, again, we start from black hole initial state I throw in a spin. After the time evolution, I divide it into 2 parts, A and A bar. But let's say if we assume the number of the dimension of this spin plus A bar is the same as dimension of A, because we assume this is a perfect tensor, we know that with fixed initial state I, there is isometry from these 3 lines, from A bar plus this spin to this. There is isometry from these 3 lines to these 3 lines. And we define this as our U total. This is essentially the Hayden-Pascal construction. And if you look at, if you just work out all the details, you'll see that in this case, what Petz map told us to do is to conjugate the operator W by this particular U total. Another thing we pay attention to is that imagine that before, if we keep the entire system, the operator reconstruction we need is U, W, U dagger, and that U is a black hole time evolution. That U doesn't depend on initial state of a black hole. But this construction, this U total depends on U, of course. It also depends on the black hole initial state I. In fact, the more qubits you lose, the more the construction depends on the initial state. So you really need some fine-tuned knowledge about the system. You need to know the initial state in order to apply the operator. Since I won't show you the details of, say, of the algebra, let's say how to write WA in this particular form. The algebra is a little bit involved, but it's not too difficult. It's basically the same as before. But I will show you some quantum circuit picture of how that this operator help you to flip the spin. Here's the initial state we have. We have initial state, black hole initial state, send in 1 spin, time evolve, and then we keep subsystem A and throw away subsystem A bar. Here's the operator we want to use. It's W conjugated by U total, where U total is in this picture is the isometry from these 3 lines to these 3 lines. So here's the U total dagger here. Then we apply W, and then there is isometry from these 3 lines to these 3 lines. So this is conjugate of W by this. This is the operator that Petz map told us to do. Let's see what this operator does to this initial state. We apply this operator to this initial state. What we get is that this U total and this U somehow they get contracted. Then we get identity from these 3 lines to these 3 lines. So at the end of the day, it looks like we send in some initial spin, then we flip it, and then we apply U again. We see that this operator just help us to flip the spin. Roughly speaking, what happened in the past when we have the entire system is that we can undo the time evolution with U dagger, flip the spin, then do the time evolution again. Now we have only more than half of the system. We can still, to some extent, undo the time evolution, but not exactly. We somehow reduce the state to the form that looks like thermal field double, then flip the spin, then go back. Before I go on to discuss the complexity of the Petz map, are there any questions? Okay, let's look at complexity of Petz map. Once we write the operator W of A in the form of U total W, U total dagger, it will be straightforward to estimate its complexity. As one can see that since W is a simple operator, most of the complexity will come from the unitary U total. So we need to study the properties of U total. If we keep the entire system, then this U total, our earlier example, that U total, that U is just time evolution. In general, this U total is the horizontal circuit stored in the black hole interior. The key property is that it can be represented as a K-local circuit, and then this K-local circuit corresponds to the wormhole geometry. That's the idea of holographic complexity, of complexity volume or complexity action duality. From this picture, we get some intuition that in this case, if we keep the entire system, then we expect the complexity is related to the volume or action from the operator to the boundary. So let's check this idea in some particular examples. We look at the complexity of Petz map and wormhole geometry under the assumption that we keep the entire system. This is the key. We look at this in particular examples of SYK and JT gravity. Imagine we have some low temperature state of SYK, which has a bulk deal of a black hole. And at time t, we apply an operator. We throw in a fermion at the boundary, which we model this by psi1 of t. And so there are two things we want to compare. We want to first we want to ask what's the complexity of this operator, and second we want to see how is this related to the wormhole geometry, that this operator will throw in a fermion into the bulk, and as the fermion gets deeper, we want to see if there's any relation between the complexity of this operator and how deep the fermion is located. In order to study the complexity of this operator, first one can look at the size of the operator. This was done in a paper by Qi and Stryker. They show that under, say, at temperature 1 over beta, the size of this operator has this particular form at time less than scrambling time. So let me just briefly comment also the definition. In general, the size of the operator is defined as the average number of fermions contained in this operator under the, for example, we say psi1 has operator, psi1, operator psi1 just have, has size 1. If we have psi1, psi2, psi3, then it has size 3. But what if we have an operator which is psi1 plus psi1 plus psi2 plus psi1 plus psi1 psi2 psi3? Then the average number of fermions contained in this operator is 2. So it's something like this. In order to define size at finite temperature, you need to do more work. Basically, what these authors did is that they first consider a thermal bath, which is represented by a Hermitian operator rho to the power 1/2. Then we consider the product of psi1 and t, psi1 of t, and rho to the power n 1/2. If we take the product of these two, the size of operator will be larger than the size of rho of top power 1/2. And then they estimate how much the size increases. And this is the result as a function of t. We see that at t equal to 0, then size is 1 as one expected, just one single fermion. As time increases during the first thermal time, the size increases as a quadratic function of time. And after that, it increases exponentially in time. I mean, the calculation was done, I think, up to scrambling time. I think what they showed is after, at scrambling time, the size will be maximal, basically the total number of fermions. And actually, in this case, maximal size is n over 2. Once we know the size of the operator, so what means we know how many fermions make up this operator, we can estimate its complexity. And in this case, one expects that the complexity grows in the same way as the size grows. Why? Because we imagine the growth of the tensor network. Let's say each circuit step, after each circuit step, the tensor network gets larger, it gets longer. And the size counts the number of nodes in the last layer of the tensor network. And the complexity counts the total number of nodes in the tensor network. And in this kind of a scrambling process, what we have is a tree. Each discrete time step corresponds to, say, each thermal time, and correspond to each layer of the tree. when you have a tree, you have the property that the number of nodes in the last layer grows in the same way as the total number of nodes in the tree. So before scrambling time, we have a tree. The complexity actually grows in the same way as size. After scrambling time, size is constant. Then one expects the complexity grows linearly in time. So this is from point of view of quantum information and also some SYK computation. This is what we expect about the behavior of the complexity of this operator. Let's look at some bulk calculation. We have empty ADS2, then we throw in we have ADS2, then we throw in a spin. This line represent, this black dashed line represent the trajectory of boundary of ADS2 if the spin is now there. If the spin is now there, then here's the boundary of ADS2 and you have a horizon here. After the spin comes in, it kicks the boundary out. Here is the new boundary trajectory. And here's the new horizon. We look at the intersection of the word line of the spin word line with the original horizon. And then we look at the distance between boundary at time t with this point. Here, we want to make some comment that why do we think that this is a reasonable point to locate this operator? If we draw the Wheeler-DeWitt patch at time t, we see that it contains the part of the word line of this spin. And we want to apply the operator to flip this spin on the entire word line. However, if you observe this geometry, we see that without this spin, this is the horizon. Without the spin, this is a horizon. With the spin, this is the new horizon. The space-time region between the two horizons, they are there because of this actual spin. So the emergence of this part of space-time is related to the gates that involving this actual spin. On the other hand, we cannot push W deeper. Why? Because our initial assumption is that, say we have, initially we have a black hole with S-1 qubits. That's all we know. We know we have black hole at certain temperature, certain charge, etc. We know some macroscopic properties, but we didn't give any information about more detailed fine-tuned knowledge about the state. In particular, we don't even know if there exists a good classical interior. What we do know is that this part of a geometry corresponds to a black hole with S-1 qubits. So let's look at the volume, the maximal volume between this point and this point. Because we are at dimension d equals 2, so the volume here is nothing but the basically grows like the geodesic distance. One can work this out in JT gravity and see that it grows in the same in the following way. It's log of 1 plus a small number times sinh squared pi over beta t. This small number is this delta S is the increase of the black hole entropy due to this actual spin. This S minus S naught is the black hole entropy minus the extremal entropy. We see that this combination will saturate. This combination start from very small number and will be of at scrambling time. This combination will be say of order 1. So for at less than scrambling time, this distance roughly is just this part, and it has exactly same form with the complexity of this operator. After scrambling time, we basically take log of this part. We see a linear behavior, which also matches what we expect about the growth of complexity. So here is the case that when we keep the entire system, we see that when we keep the entire system, then the operator reconstruction, roughly speaking, is just because there is a horizontal circuit laid in the interior. You just undo the horizontal circuit, apply the operator, then go back. In this case, there is a correspondence between the complexity and the location of the how deep this operator is located. But we will lose this good relation once we only have part of the system. So if we only have part of the system, Hayden-Press code told us that we can still reconstruct the operator, but naturally, one would expect that it will cost us higher complexity. The reason it will cost us higher complexity is because, let's say, there is some horizontal circuit stored in the black hole interior corresponding to the wormhole geometry. It is a k-local circuit. Because it's a k-local circuit, so the complexity roughly just corresponds to volume. But once we write down the Petz map as U total, W, U total dagger, that U total may not be k-local. That U total is constructed out of U, but it may not be k-local. Because it may not be k-local, as a unitary operator, there is a chance that it will have high complexity. And this is essentially what Python's launch discussed. So let me very briefly review Python's launch. It's from a paper by a group of people from at the end of last year. And it's also based on some earlier work in 2013. Complexity volume or complexity action told us the complexity of tensor network. Let's say if the tensor network has a corresponding wormhole geometry, then the complexity of this operator just counts the number of nodes in the tensor network. So naturally, it just corresponds to the volume of the wormhole. But there is one special case, is that when, let's say here, I just draw a picture of, say, for example, a wormhole geometry. What if in the wormhole geometry, you have a bulge in the middle? I mean, there is a neck with smaller area here, smaller area here, but here there is a cross-section with much larger area. The discussion about Python's launch, first of all, they call a shape like this as a Python's launch. I mean, launch because there's launch here. And the discussion in this paper pointed out that when you have a wormhole geometry like this, the complexity of this operator no longer just grows like the volume of the wormhole. There is a, questions? There is an extra enhancement factor, which is given by exponential of 1/2 A max, this maximal area, minus AR. Let's say when you have a geometry like this, then maybe, let's say the RT surface is located here. And from the entanglement wedge reconstruction, we know that we can basically reconstruct the geometry in this part. However, because of this particular shape, the complexity is no longer just given by the volume of this wormhole geometry. Instead, there is an extra enhancement here. This is the story about Python's launch. In our story, I mean, we wrote Petz map in the form of U total W, U total dagger. And let's look at what this operator does. We assume the black hole initially has S qubits. So here S is 5. There's 4 lines here, or 1 line here. And we call N the number of qubits in A bar. So N is the number of qubits that one loses access to. And U total is defined as an isometry from this 3 line to this 3 line. So there, and then we see that we just draw, we look at cross-sectional area at a different part of the tensor network. We see that here, there is a bulge here corresponding to cross-sectional area S plus N. and then there is a smaller neck here, corresponding to area S minus n. And this part also corresponding to area small S minus n. So smaller area, larger area, smaller area. What we see is exactly the Python's lunch scenario. And if we just use the conclusion of Python's lunch, what it tells us is that in this case, the complexity, I mean, other than the volume factor, the complexity will have extra enhancement, which grows like 1/2 of the number, the entropy corresponding to this area minus the entropy corresponding to the smaller area, which grows like e to the n. Now we see that this case, when we only have part of a system, there is an enhancement of the complexity, which grows in exponential of the number of qubits one loses access to. So it's the number of qubits in a bar. Let's look at this in more detail and just get some intuition about that, where this extra enhancement come from. Let's ask the question that how do we apply this operator U-Twiddle dagger? Here is what we want to do. We start from S minus n qubits in state I. We want to map it to a state like this. And this U depends on the initial state I. Here is the tensor network here. Here is our initial state, S minus n qubits. And there is one way to easily, looks like it can easily achieve this operator, to apply this operator, is to do this. Let's say we start from S minus n qubits. And then we take n Bell pairs. And we combine 1/2 of the Bell pairs with this S minus n qubits. So we have S qubits here. Then we apply U-Twiddle dagger. Oh, sorry, apply U dagger on this S qubits. Recall that U is a K-local operator. U is not too complex. U is the operator whose complexity corresponds to the volume or action of the black hole. Afterwards, we get S qubits out. Then on S minus 1 qubits, we do a projection to post the selected initial state. Recall that we mentioned earlier that this U-Twiddle actually depends on the initial state of black hole. We do the post selection on the initial state. Then we see that what we get is exactly the state we want. From this point of view, it looks like this operator is not that complex. But the key point here is that we need to do this post selection. We need to do this projection. And projection is not a unitary operator. If we want to achieve this in the form of the unitary operator, the complexity can be much higher. So if we allow projection, then it looks like they basically roughly have the similar complexity with U. But if there's no projection, then what one can do is to do something like similar to Grover's search. What happens is that one can go back and forth and apply this U-Dagger many times, and each time we slowly rotate our state such that at the end of a day, our state is gradually rotated to this target state. And how many this kind of back and forth do we need to do? We need to do this. The number we need is e to the power n, depends on the number of post selections we need here. So that's why there's a Python. That's why as a unitary operator, U-Twiddle will have much higher complexity than U. Are there any questions? Okay, then I will give some summary about, about some comparison between exterior operator reconstruction. Recall that at the very beginning of the talk, we mentioned that if you just look at the complexity of HKLL reconstruction, then naively one would expect that the complexity actually blows up as one approaches horizon. Then how come we just then talk about all this complexity of, say, Petz map reconstruction. Somehow we get a finite number, and under certain circumstances, this number is actually not that large. What's going on here? The resolution here is that we need to differentiate between two different concepts. One concept is the complexity is to, let's say, I give you a boundary state. You figure out what operator to use. Another concept is that once I know what operator to use, then we apply this operator. And these two concepts can give you completely different answer. I mean, there was some recent work on computational pseudo-randomness. What it says is that one can efficiently create ensembles of quantum states that are exponentially complex to distinguish from random. So what this tells us is that first, these ensembles of quantum states can be easily constructed. One can efficiently create that. So none of them will have a very high complexity. But on the other hand, it's exponentially complex to distinguish from random. That means even though I create this ensemble of states easily, I don't know they are easy. I don't know they are simple state. We don't know what they are. In particular, recall that in the Petz map reconstruction, we need fine-tuned knowledge about the state in the sense that we need to know how the co-subspace is embedded in the boundary Hilbert space. Petz map made use of this V, and this V is the horizontal circuit stored in the black hole interior. In general, it's hard. I give you a boundary state. It's hard to figure out the horizontal circuit stored in the interior. If we compare this with the exterior operator reconstruction, I mean, if you want to apply an operator in the exterior, what do we need to know? We need to know, say, the temperature, mass, or charge of the state. Roughly speaking, we need some thermodynamic quantities of the state, and that basically determines the geometry in the exterior. Then we can use HKL reconstruction. It's not hard to figure out. But once you want to construct the operator in the interior, it crucially depends on that embedding of co-subspace V, and it's very difficult to figure out what that V is. Once you figure that out, then the reconstruction may or may not be very complex, depending on that, do you have the entire system or you lose access to the part of system? If you have the entire system, then what you do is just basically undo the horizontal circuit, apply the operator, then go back again. But when you don't have the entire system, you lose part of the system, then the Python's launch scenario appears. What you do is you can still somehow shorten the wormhole, go into the interior, but in a way that's much more complex. How complex it is the complexity grows exponentially in the number of qubits you lose access to. Here's the end of my talk. Thank you.
Okay, thanks very much, Ying, for a very nice talk. Are there questions from the audience? Okay, if there are no questions, I have a question.
I think
oh yeah,
there was a raised hand of Shira.
No, that was a clapping sign. Sorry about that.
Okay, I have a question of my own. If there's no other question from the audience. Hello?
Hello.
Yeah, so this is again revisiting the HKL story. So at least for the two-sided black hole, it was known that you can construct a local operator in the interior if you use smeared operators on both boundaries, on both the left and right boundaries.
That's true, but here, yes, that's true.
So can you not estimate the complexity of something which is in the interior by looking at patches on both boundaries?
Both boundaries?
Yeah, so the idea is that in HKLL, if you have a two-sided geometry, then interior operator is given by a smeared operator, which is
Yes.
the disjoint smearing on the left and the right boundary.
Yes.
I'm not sure if you're familiar with that. So can you not estimate the complexity of a local operator in the interior using that HKLL prescription?
Using that HKL reconstruction.
Yeah. So it doesn't use single boundary; it uses both boundaries.
I think so, but I think I still think you encounter this kind of a blow up of complexity. The reason is, let's say if you have thermal field double, you write the operator, you first do backward time evolution and write the operator, say, on a particular spatial slice, right? And this spatial slice actually go across the horizon. And but once you approach the horizon, the complexity blows up.
Okay. And I have one more question about the Petz map itself. So this Petz map supposedly reconstructs something which had entered the horizon or something which went inside the horizon. Can you tell me if this reconstruction, using this Petz map, is it local? That is it microcausal? That is, if I want to reproduce or construct an operator inside the horizon which commutes at space-like separations with anything else, this Petz map, does it respect this microcausality?
So what do you mean in the sense that microcausality?
It's something which commutes at space-like separations. If you have two operators, for example, one inside the horizon and one just outside, but they're space-like separated, they would commute at space-like separation. Does the Petz map reconstruction, which you described, does it respect this microcausality?
So if I put this, okay, if they are inside the same co-subspace, then yes. Why? Because the construction I showed you that basically you write the operator as a conjugation by some, say, U twiddle, WU. Let's say if you have W1 and W2, if initially they commute or they don't commute, I mean, this kind of conjugation respect the same algebra if they are in the same co-subspace. But what if, say, they are very far away separated, and if they are, and in that case, can they be put in the same co-subspace? I don't know.
I see. Okay. Okay, are there any more questions? Okay. So if there are no more questions, we can thanks Ying for a beautiful talk.